Hi geometry students, welcome back. This is Mrs. Brunk. Today we're going to be kind of looking at the opposite lesson from the prior lesson, which was lesson 9.3, and that was properties of rectangles, rhombuses, and squares. And in today's lesson, we're going to learn what conditions a parallelogram would have to meet in order to be classified as a rectangle, a rhombus, or a square. So our learning goal today is we will be able to use the conditions for rectangles, rhombuses, and squares to determine if a quadrilateral or a parallelogram is a rectangle, a rhombus, or a square. Okay? So just like when we did this with parallelograms, we first learned the properties of what a parallelogram possessed. So if this thing's a parallelogram, it has all these traits, right? And then in the next lesson, we turned it around and we said, okay, well, we've got this figure, and we don't know if it is a parallelogram, but we want to know, is it one? And so we say, okay, what would be the minimum criteria that it would have to guarantee that it would have to be a parallelogram? Well, we're going to do the same thing with rectangles, rhombuses, and squares, but they have different criteria, of course, because they're more specialized figures. So the first thing we're going to look at is conditions for a rectangle. So you're looking at a figure, you think it looks like it's a rectangle, and you want to know the minimum information you'd have to know to be able to know for sure and say without any doubt that, oh, well, this thing is a rectangle. And here are the two conditions. Number one, if an angle of a parallelogram, so it would have to be a parallelogram, but if one of the angles is a right angle, then the parallelogram would have to be a rectangle. So notice it only says one angle would have to be a right angle. And that's the reason why that is, that's the minimum you'd have to know, because if you know that this one angle is a right angle, then you'd know that the angle across from it would have to also be a right angle, because opposite angles in a parallelogram are equal, right? And then you'd know that angle B and D would also have to be right angles, because consecutive angles in a parallelogram are supplementary. And if you already have a 90-degree angle right here, then the angles that are next to this angle A would also have to be 90 to add up to 180. So instead of having to reason through all of that every single time, we now have a theorem that says if one angle of a parallelogram is a right angle, then the parallelogram is a rectangle. And that's because if one is a right angle, all of them have to be right angles. So that's our first condition. So again, these are like minimum requirements to make something be a rectangle. Number two, if the diagonals of a parallelogram are congruent, then the parallelogram would have to be a rectangle. Okay, so again, you're starting off with this information. It's a parallelogram here, and you think it might look like it's a rectangle, but they don't have that telltale sign, which is the four right angles in it, right? If it had the four right angles, there's no question. It meets the definition. But we don't have that here, but it certainly looks like a rectangle to me, so what is the minimum information I'd have to know? Well, if I knew that these diagonals right here were the same length, so if I knew that AC was equal to BD, that's enough. Then I would know this has to be a rectangle. So let's take a look at applying that and see if these figures meet the criteria to be called rectangles. So notice that all the given information for every one of these is these are parallelograms, okay? So we already are starting assuming we know these things are parallelograms. They're telling us that up front. And then they're giving us this additional information. Let's see if it's enough, okay, to meet one of those two criteria we just learned. So I'm going to mark all this stuff on the drawing. So it says that EF, so here's EF, is equal to GH. It tells me that FG is equal to HE. And it tells me that FH is equal to GE. So what I want to know is that enough information? So this right here is equal to this one right here. Is that enough information to guarantee that this has to be a rectangle? So in the chat, I want you to say yes or no. So do you think this is enough to prove that this is a rectangle? So yes, this actually is enough information. In fact, they gave us way too much information. We really didn't even need to know these first two things. This was the kicker right here. Knowing that the two diagonals, FH and GE, were equal meant that it satisfied this one right here, right? It satisfied the fact that if the diagonals of a parallelogram are congruent, then the parallelogram has to be a rectangle, right? Telling that the opposite sides were equal really just told us, just reconfirmed that this was a parallelogram. But I needed that fact about the diagonals, or to maybe that it had a right angle in it, in order to prove that it was actually a rectangle. So yep, this is enough information because the diagonals are congruent. And that meets that one of the conditions for a rectangle theorem. So diagonals are congruent. So that's a yes. All right, so looking at the next one, again, we're always assuming these are parallelograms. We're told they are, but we want to know, are they specialized enough to actually be considered a rectangle? So it says angle FEG. So let's see, FEG, that's this angle right here, right there, is 45 degrees. So this, I'm going to color this one in right here. That one's 45. And then it says GEH. So GEH is right here on this side, and this is 50 degrees. So based on that information, is there enough information to say this is a rectangle? So tell me yes or no in the chat. Do you think this makes this a rectangle? So that was, again, a resounding agreement by people. That was a no. I did see one yes with a question mark, but so whenever you do that, that just means if you're questioning it, you're probably right. You're probably that it wasn't yes. So this is a no, and that's because if you the two angles together, this makes 95 degrees, right? If that angle is 95 degrees, then there's no way this could be a rectangle because those angles all have to be 90 degrees, right? So that angle, angle E, is not 90 degrees, and so we know that that's not a rectangle. Yep. Okay. So we can use those conditions also to disprove that something is a rectangle as well. So if they don't meet one of those criteria, then nope, we can't show that it's a rectangle. Okay, so then the last example here, so ABCD is a parallelogram. So again, it's given that's a parallelogram. And then they give us this information, that ACD, so let's see, ACD, that's this little angle right in there, is 25. And angle ACB, so ACB, this angle right here, is 65 degrees. That's all they give us, and we want to know, is this enough to be a rectangle? So yes or no in the chat. Okay, so there seems to be a little more disagreement on this one. I saw lots of yeses and lots of nos. And if I look at the two angles that are next to each other that are making that little corner angle at C, 65 plus 25 adds up to 90. So we've got this 190 degree angle, and hey, that's what that theorem said. It said that's enough, right? It said if one of the angles is a 90 degree angle, then that's enough. And the reason why one 90 degree angle is enough, I know that doesn't feel right because you're like, oh no, the definition of rectangle is 4 right angles. But the reason why is we already know this is a parallelogram, so if this angle is 90, then A would have to be 90 because that's the opposite angle in a parallelogram, right? And then B and D would also have to be 90 in order to add up to 180 degrees. So just knowing that one 90 degree angle, that's it. That's all I need. And yes, so it's got at least, or it's got, I guess I should just put one. It has 190 degree angle is given. And that's enough. With it already being a parallelogram and then throw in, oh, there's a right angle there, that does it. That's enough. So now we're going to look at the conditions for a rhombus. So in order to be enough information to prove something is a rhombus, so similarly to how we did this with the rectangle, if we know it's a parallelogram and one pair of consecutive sides of a parallelogram are congruent. So notice if you look at these markings on here, and I would maybe on your notes highlight this. Notice how they're only showing one pair of consecutive sides being equal. Okay, but we know a rhombus has all 4 sides equal, but that's okay. I mean, we can reason through that, because if this is a parallelogram and we know this fact that EF and EH are equal, well then we could go through and reason, okay, well then that means that the sides opposite them would have to be the same length because it's a parallelogram, right? So that's actually the minimum we'd have to know, is that we have a pair of sides next to each other, or consecutive, right? That's what consecutive means. It means next to. If you want to write next to in your notes above consecutive. So two sides that are next to each other that are equal, then that would actually guarantee that they're all equal, and then it would be a rhombus. So that's the first condition for a rhombus. Another one is if the diagonals of a parallelogram are perpendicular. So you got a parallelogram and you see that the diagonals make 90 degrees in the middle. So you can see that they're perpendicular, okay? Then the parallelogram would have to be a rhombus. So all you have to be able to do is identify in a parallelogram that the diagonals make 90 degrees in the center there, and that's enough. Then you know, oh, it's a rhombus, right? So that's the minimum requirement. And then the final way is if one diagonal of a parallelogram bisects a pair of opposite angles. So see here, this is one of the diagonals, right? And see how it's, oops, I didn't draw that very good. Let me redo that. Draw that again. So see how it's bisecting the angles because they're marked equal on either side? Those little arcs are saying that those are the same measure, right? Oops, I'm going to get that one a little better. So because I know that it's actually bisecting the angles at the ends at F and H, that's actually enough to show that it's a rhombus, okay? Because then we could reason through and show that if it bisects those angles, and then it would also, we can kind of logically go through it, and we know that the other diagonal would also have to bisect the angles at the other ends at E and G, okay? So again, the minimum requirement is to have one of these or the other. And just like we did with parallelograms, we don't have to show all of them, okay? We want to do as little work as possible. So I put ors between these because I just have to show this or this or this. One of these three things, along with it being a parallelogram, that's enough then. Then I can say it's a rhombus, okay? So let's test this out. So given that, and again, in each one of these, we're told these figures are parallelograms. We at least know that, but we want to know, are they also rhombuses, okay? Oops, and this says, to determine whether the quadrilateral is a rectangle, let's cross this out and write rhombus. I imagine what we did was, did a copy-paste, and we just forgot to change that to say rhombus. So fix that, please, so that we know we're looking to see if these are rhombuses. Because clearly these are not rectangles. So the given information beyond the fact that this is a parallelogram is that JK, that's marked on here already, right, and KL are equal. So enough information, yes or no? Just drop your answer in the chat if you think this is enough to make it a rhombus. Okay, so let's look back at this conditions and notice the very first one said all you have to have is for it to be a parallelogram and have a pair of sides next to each other be equal. And that's exactly what we have right there, right? Okay, it's the different pair of sides marked, but it's still the sides that are next to each other. So yes, this is, yep, this is because one pair of consecutive or next to consecutive sides are congruent. And so we meet that first part of the conditions theorem. The next one, okay, again, so we know this is a parallelogram, and then they give us this information. Angle BCA, so BCA, that's this one, is congruent to DCA, DCA, okay, and that BAC, so that's down here, is congruent to DAC, down here. And in fact, actually, I could have marked them all the same because if you think about this, we know this is a parallelogram. These opposite angles have to be the same, right? So if they're saying these parts on either side are equal, then that actually would mean that this is, oops, I got to erase this. Oh, let me erase. That they're actually all the same there, like that. So is this enough information to prove that this is a rhombus, yes or no? So I'm definitely seeing more yeses than nos, and in fact this is a yes. This is another one of the yeses, and I can show you back again if you look at the theorem. The one that actually supports it is this one down here. If one diagonal of a parallelogram bisects a pair of opposite angles, then the parallelogram is a rhombus. And that's exactly what's going on here, because this diagonal right here acts as a bisector to those two opposite angles, and that means that it meets the criteria. So diagonal, to give a support, we'll say diagonal bisects pair of opposite angles. So that would be our reason. It's that third part of the conditions for a rhombus theorem. Okay, so now this figure's starting to look more, this one's starting to look like a square, but I haven't learned any ways to tell for sure if it's a square. So they want to know it's a rhombus. Okay, so it says this is a parallelogram, and that KM, so KM, which is right here, and LJ are perpendicular. And it says that LNM is 90 degrees. Now, they didn't really have to tell us that that was 90 degrees because they already told us that the diagonals were perpendicular. So that's kind of implied. If they're perpendicular, they make 90 degrees. So is this enough information to prove that this is a rhombus? Okay, that the diagonals make 90 degrees in the center. Yes or no? Okay, so there definitely seems to be agreement here that this is a yes. And again, if we refer back to the theorem, we can tell that the reason for that is this one right here in the center. If the diagonals of a parallelogram are perpendicular, then the parallelogram must be a rhombus. So it meets that. So we've got our reasoning, our support here would be to say the diagonals are perpendicular. And you can use the symbolic way of saying that, like the upside down T, or you can write the word perpendicular. But we can tell that their diagonals are perpendicular, and that's enough then. So that actually does it for today's lesson. It really is just, notice that there wasn't any like conditions for squares. Now, in order to be considered a square, you would have to be able to prove that it meets a criteria for a rhombus, and at the same time, it would have to meet one of the criteria for a rectangle. So that's much harder to do because in order to be a square, you have to be the most specialized quadrilateral, right? So you'd have to maybe say, be able to show that there's at least one right angle in it, and then maybe show that the diagonals are perpendicular, or show that there's a right angle, and then maybe that consecutive sides are equal, or show that the diagonals are equal and perpendicular. If you can find one criteria from each of these, from rectangle and rhombus, that for a figure that's a parallelogram, then you can say it's a square. So that would be the only way, is to use these two theorems together in order to prove the most specific kind of quadrilateral, which is a square. So that does it for lesson 9.4. Thanks for coming to class.